Now that we've grappled a bit with how raster model data work, vector model data work, we can grapple a little bit with how we create raster data, and especially in this case, remotely sensed data. And really, we want to grapple with why we're dealing with all of these different wavelengths, this different energy. As previous videos have discussed and pointed out, raster remote sensing data is patched together from satellites that are sensing electromagnetic energy at different wavelengths. Each sensor is tuned or built to sense data at certain wavelength snapshots, certain slices. So you might have a red band and a green band and a near infrared band and all this other stuff. Because we can see certain things in these electromagnetic spectrums that we couldn't see otherwise. Part of the fun about remotely sensed data is that we can see stuff beyond the visible light spectrum, which you can see on the left here. Different plants, different features in the soil or minerals or water or whatever show up at different wavelengths. And there are some that are ultraviolet. So it's not just that we're going below, longer than the visible. We're going shorter than visible too in some kinds, but for plants especially, we are very interested in the near infrared and the shortwave infrared, so on and so on. So, for example, here we are seeing the world in the infrared, where we see differences in minerals, differences in the nature of the landscape that we couldn't see with just visible light. In this case, we can see some lake shore here in Western Australia. So we see the water. Maybe we're seeing more details about the water than we would visually. We see differences in the landscape. Vegetation, rocks, minerals, something like that. Here's the Atlas Mountains in Morocco. Huge swath of the landscape. You can see the scale bar down there, 10.4 miles. Again, different minerals, different morphologies, different features because of the bands we're putting together. More mountainous area, this time southeast on the way southeast on the African continent in Tanzania. We can still see some of the topography, some of the features. But now we're especially seeing kind of different histories of these mountains, different geology, stuff like that. Differences in these type of wavelengths or these type of combinations of bands and stuff can also reveal to us different textures. Texture is one of those things that's really interesting to think about in remote sensing data, in raster data, because it's something that we can definitely, we know what we mean by texture. Look at that on the left. You're looking at palm plantations. They're interceding diagonally into a more native forest type. The texture is different, just like the urban texture is different in our Jersey suburbs here on the right. Suburbs in New Jersey, in the United States. Texturally, we get different information when we combine bands. Here's a beautiful texture in the Namibian desert. We can see the sand dunes. We can see the flow of water. We can see the differences in the landscape. And we couldn't see this if we were just looking at a visible light picture. So why are we not just looking at visible light pictures? Because false color is everything. We can see such a narrow slice of what is happening in the universe, what is happening in the planet. Much like an X-ray observatory can see far off quasars doing weird stuff. An infrared observatory orbiting our planet can see weird stuff going on here. Now, we do have to represent false colors as colors we can see, so there's a translation piece there. But all of this other information is super valuable. Salton Sea, California. Color, false color. Well, let's sit on this for a minute. Most satellite data is captured in bands, right? And so you have red band, green band, blue band, so on and so on and so on. So when you're making up these pictures, you're literally just combining bands together like an old cathode ray tube television. So I guess plenty of extended discussions in remote sensing classes. This is not a remote sensing lecture or a remote sensing class or a remote sensing playlist. We're just talking about it because it's part of GIS and we have to. This is, I guess, technically a false color because it is RGB. It is not a panchromatic. It is not like our eyes see. Anyway, here's a falser color that is highlighting the near band. Double false color. And since vegetation pops out more in the near infrared, if you replace the red band, so RGB, red, green, blue, if you replace the R instead of red like our eyes can see with near infrared, like our eyes can't see, oh, that vegetation pops. Pop. And we could emphasize it, we could then retool it and say, okay, we'll actually make it green. And we could show the near infrared is green and then the longer infrared is red, right? So you can play around with all of these. Check out, there's a pond right below the lake here, kind of bottom center. That when you start really making a false color and replacing more of those red, green, blue bands with infrared light, just pops. Something about the salt, something about whatever's going on mineralogically, something going on with the minerals there. One of the very common ways, and what we've been playing with a little bit, and what really the satellite era has allowed to develop, is NDVI. There's one remote sensing term to be familiar with at the conclusion of a GIS course like this one. It is NDVI. Normalized difference of vegetation index, which essentially takes your NIR band value. Remember, going back to this, each of these are pixels. Each of these pixels have a value. There's the measurement of the reflection of this energy that the satellite has detected, often adjusted for atmospheric influence and whatnot. In any case, you take the value of your NIR pixel and you subtract the red pixel, and then you divide that by the sum of the NIR pixel and the red pixel. And that gives you NDVI. And from that, we have a scale. We can tell what is vegetated, what isn't. And if you have that calculation for the same place over time, you can tell differences in vegetation. That's pretty cool. So NDVI is just a simple calculation of two values, an NIR band and a red band. Subtract that, NIR minus red, together, divided by NIR plus red together. And all of a sudden, you have much clearer measurements of where your vegetation is. What is abundant vegetation? What is healthy vegetation? How are vegetations changing? Now, it's tough to tell the difference between vegetation types unless you start to get really precise, very narrow bands. That's called hyperspectral remote sensing. It is definitely not something we're saying any more about. It could be done, I suppose, if you have the data. So sometimes you can't differentiate the type of vegetation, but we could look seasonally. We could understand greenness as plant populations change. We can see green up and green down. We can see spring and fall and those changes over time. Now we can see this with our eyes, right, of course. Go back in time. But with NDVI, we can actually track and measure this. And we can say, okay, here in New England, when do the leaves appear? What day of the year do the leaves usually show up? Oh, and if that changes over time, could we measure that difference and find, say, a signal of climate, say a signal of forest health, vegetation health, impacts of storms or of droughts. All of these different things are possible when we use our data and when we model our data to understand what the spectra are telling us. This is called phenology very broadly. You don't have to do phenology with remotely sensed data. National Phenology Network takes a lot of different measurements and readings. When the lilacs bloom is a very common phenological data source. Honeysuckle in the South, the US South. When the buds show up, when the leaves start to turn color and fall. These data representations, again, are abstractions. That's what GIS is all about. But these GIS abstractions allow us to connect with understandings of climate change, understandings of land cover change, understanding of how we change the earth over time. And that's possible because we have such a rich history of satellite data.